All right, let's start the chapter 10. This chapter is about the correlation and the regression, but it's just the introduction of the correlation and the regression. We will only talk about a little about this topic. So let's start with the correlation. So in this section, we will introduce one concept called the linear correlation coefficient R. So this R is just a value. This value measures how stress the linear relationship between the values, between the variables. Okay, so first we should know it's just the linear relationship, which means we will try to fit all the data. We will use the straight line pattern to fit the data. So that's called the linear. Okay, but the most important part here, we will use the paired data, which means for each observation, we have two measures. So for each observation, we will have two values, and these two values are paired. Okay, so we call it bivariate data. So each observation actually have two values. Each sample will have two values. And we only consider linear relationship. We only measure the linear correlation stress by using the R value. So first, let's check what is the definition of correlation. So just like I said, each sample we will have two values. That's two variables. And one variable, the value of one variable, are somehow associated with the other variable. So these two variables are not independent to each other. One is related to another one. So we call the relationship is kind of like a correlation. So that's the basic definition. And we can have all kinds of correlation, right? It can be nonlinear, it can be linear. And we only talk about the linear correlation here. There's a correlation between two variables, and the plotted points of the paired data can be expressed by a straight line, approximately by a straight line. So straight line means linear, right? Their relationship can be approximately by a straight line. Then we got linear correlation. Let's check some graph to help you understand. So for each point here is just one sample, one observation. Sorry, not one sample. It's one observation in our sample, right? And each point you can have a value of X. You can also have a value of Y. So make sure you understand each observation you will have two values. So the X value we can find here, and we can also find the Y value. So we could use the scatter plot to draw all of the points in this sample, right? And we will say it is approximately a straight line. And this straight line is positive. We know for this kind of shape, we will know the slope is positive. So we will say it's the positive correlation, linear correlation between X and Y. Okay, so the slope tells us it's positive. So this one, we also can use a straight line to approximate all the dots, right? But this time the slope of the straight line is negative. So we will say it's negative linear correlation. We check, we will get a negative value for the R. But for this kind of scatter plots, I see I cannot find a straight line to approximate all the dots. So we will say there's no correlation between X and Y. No correlation between X and Y because it seems random, right? We cannot find any pattern. So we will say it's no correlation. Let's check another kind of one. Yeah, we find there is a pattern for all the dots, right? There is a pattern. But if we try to connect all the dots, we find it's not a straight line. It's not a straight line. Remember, we only focus on the linear correlation between X and Y. But this one has the correlation between X and Y, but the correlation is nonlinear. So we will say it's nonlinear correlation. And we will realize the R value is not high. So we have different kinds of correlation, right? The first one, we can find a straight line. So, and the slope tells us it's positive correlation. Similarly, the second is also a straight line, but tells us it's negative correlation. But this one, we cannot find any pattern, so we can say there's no correlation. The last one, although there is a pattern, there is a correlation, but we can find the shape is not the straight line, so we will call it nonlinear. So we can measure the stress of the linear correlation by using the linear correlation coefficient R, by using the R value. Measure how good is the straight line fit all the values, right? So the stress of the linear correlation between the X and Y, again, for each observation in the sample, we will have one paired values. So that means we will have two values for each observation. So we will learn how to calculate the value of R and how to interpret our R value. But for the hypothesis testing part, we will just ignore that. So we only need to use the R value to determine if it's a linear correlation between two variables. Let's check the notations first. Okay, here the number n is the number of pairs of sample data. So for example, I have several I have 10 sample, 10 observations in the sample. So 1, 2, 3, 4 until 10, right? For each observation, the first observation, I will have a paired value, which means I will have one value for the first variable x, and we will have another value for the second variable y. So for each observation, the first observation, I will have x1, y1. For the second one, I will have x2, y2, and so on. We'll have x10, y10. So you will realize it's a pair. We actually have two values for each observation. One is x, one is y. Okay? But the n here is not how many values in total, not 20, it's still 10. Tells us how many observations, just like on the graph, how many dots do we have? So sigma is just the sum, the addition, okay? Sigma x means I will find the sum of all the x values, So here, if I put sigma x, then that will be x1 plus x2 plus x3 onto plus x10, right? So this is the sigma x squared. So remember, you compare this two notation. This is sigma x squared. This is still the sigma x. Then take the square. Let's check the difference between these two. First one, we should get the square value of x first. Then we should find the sum. So you understand this? This part, we should get the squared x value first. So for the first one, I have x1. Then I find the x1 squared. I write down the value of x1 squared. For the second observation, I have x2 squared. Then I list 10 x squared value. After that, I should find the sum of all these 10 squared x values, right? So I would find the square first, then do the addition. But the second one, I will find the sigma x, find the sum of all the x value first, then find the squared sum. So make sure you do not mess up this too. Okay? This is find the squared first. After that, get the sum of 10 squared x. This one, find the sum first, then take the square. Okay, so similar here. For this one, each x1, y1, I find the product first. For the first observation, I find the product of two values, x1 times x times y1. For the second value, I will find the product x2 times y2. After I list all of 10x times y, after that, I try to find the sum of all the products. Okay, so here, the R, we know it's just the linear correlation coefficient, but make sure you know this is still the statistic. It's still the statistic, so it's from the sample. For the sample, it's the notation for sample. Of course, we have the corresponding population linear correlation coefficient, but here it's not a lowercase p, so it's looks like p. Actually, it's rho. It is called a rho. Okay. So let's check before we calculate the R value, we still need to check the requirements, but we just quickly go through this part. Okay. Of course, all of the sample should be the simple random sample, and we only can have quantitative data. So if it's just a word, then we cannot use the word to find the linear correlation coefficient, right? It should be a value, should be a number, right? Numerical meaning value. Let's check the scatter plot. So from the graph, we should find the pattern, and the points can be expressed by a straight line pattern. So first, we should try to draw the graph, draw the scatter plots to see if there is a straight line we could use to express all of the points. Okay, it's not necessary to be a perfect straight line, but it should have that pattern. So I should remove all of the outlines, which means this R value is very sensitive to the outliers. It's very sensitive to the extreme values. We should remove all of the extreme values, or we say remove all the outliers. Then we could do the Now let's check the formula. How can we calculate the R? So this is, let me see. Okay. This is the good format for calculation. You think this formula is complicated, right? But actually this one is already easy to calculate. Remember when we talk about the notations, we know what is the n? It's just the sample size. It's just always the sample size. How many observations in our sample? But this time it's not the number of the total value, right? Because for each observation we will have 2. So if we have n equals 10, we will have 10 x values. We will also have 10 y values. So total we will have 20 numbers, but actually n is still equal to 10. This is a common mistake, okay? When you calculate, make sure you understand. N is 10, but we have 10x, 10y, we will have total 20 values. So for the first term we check, it's just find the product of x, y value first, then find the sum. Minus the sum of all the x value times the sum of all the y values. So we can list a table to write down all of the values we need. After that, we could plug into the formula to find the R value. Because this one looks simple, but actually it's more complicated to calculate. Because for each one, we should find what's the z value. We should use the z formula to find what's the z-score for corresponding to the x. So each time we should use the z formula. So it looks simple, but actually complicated to calculate. So the round-off rule is just 3 decimal places. Round-off rule is just random. So we could skip this slide. We will not use the p-value method. And we do not use the critical value method because this part is just for the hypothesis test. We will talk about the properties of the linear correlation. Okay, so the value of R is between 1 and the negative 1. From negative 1 to 1. So it can be negative 1 or 1. Then the second property is if all the values of either variables are converted to a different scale. So if first times I measure the x, for example, like the length, let's see, if the first variable I call it's just the length. Maybe first time I measured it in the miles, okay? So then I list all the values here. The second time I measured all the x use the kilometers. I list all the values, which means the variable converts to a different scale, but the value of R will not change. So their linear correlation will not change. Okay, the linear correlation, the first time I measure x and y into one scale, then second time I use another scale, but their linear correlation will not change. And you could even switch the order of x and y. You can treat the x to be y, and you can treat the y to be x into your formula. Then the value will not change. So which means their linear correlation will not change. Even you change the order of x and y. If it's still about these two variables, then their linear correlation is always the same. Again, R only measures the stress of linear correlation. Okay? It cannot measure all of the correlation. If you have a correlation which is nonlinear, then you cannot use R to measure the stress. Okay, another one is very sensitive to the extreme values. So before we get to the value, we should remove all the outliers. Let's check this example. So for easy calculation, we only list 5 paired data values. So again, you see, how many values do we have in OR? We have 5 values for chocolate. So maybe we say X is the chocolate. Y is the Nobel Prize, right? It's the Nobel Prize. So we have 5 values for X and 5 values for Y. 10 values in total. But remember here, I said N is just equal to 5 because this is our first paired value. This second, we total only have 5 paired. 5 pairs. Okay, so make sure you understand N is equal to 5, not how many values do we have. We want to use this table to find the value of R. Of course, we could use technology because the calculation is not simple, right? We can always use the technology, but you should know how to find the answer in your output. So let's see, this is the R value, and this is also tell you the R value. It's easy to find the R value, right? But in our class, we will focus on how to use the formula. How to use the formula to find the R value. So I would suggest you list the table. List the table. Because if you go back to check the formula, you realize you're gonna need the value of sigma x. You will use the y value for sigma y, and you're gonna use the sigma x squared, sigma y squared, and the sigma xy. So which means you should list all of these values. Then you can use these values, plug into your formula. You can easily find your answer. But make sure you understand the N is not the total number you have. It's just how many observations, how many pairs do you have. So in this case, we have x1, y1, x2, y2, and we total have 5 pairs. So we list all the values for chocolate. Chocolate is our first variable. I will pick chocolate as X. But some students will say, if I pick Nobel Prize as X variable, is that okay? I will say it's totally okay. Remember when we talk about the property of the R, if we switch the X to be Y, change the order of X, Y, well, the the value of the R will remain the same. So if you like chocolate to be your Y and the Nobel will be your X, you will always get the same value of R. So it doesn't matter. We just treat the first value we have to be the X and the second to be the Y. So I list all the values here. The chocolate consuming, I will fit 5, 6 list, then list all the Y value here. Now the third column, I will put X squared. So how can we get 25 squared? The first X value 5, we get 25. And the second squared X will be 6 squared, so get 36. So this whole column is for the squared X value. Similarly, this whole column is squared the Y value, right, to get it. And the last column to find the product of each X and Y. So for example, the first one, X is 5, Y is 6, 5 times 6 will get 30. So last row will be the sum of the whole column. So 5 values for X, so the last column will be the sum of all the X values. We say it is the sigma X. And this column, sum of all the Y values will be sigma Y. Similarly, sigma X squared, sigma Y squared, and sigma XY. Now we finish this table. We only need to focus on these 5 values. We're going to use these 5 values to plug into the formula to find our answer. So this is the formula we're going to use, right? So it missed some parentheses. So make sure you check your textbook for the parentheses we miss. Okay. So plug it into the formula. By using the previous table, we will get this value. We will get the value of R. Okay? So let's check the solution. So here we know that X variable is just the chocolate and the Y variable is Nobel. Of course, you can also use this way to find it, but each time you should use the Z formula. So I will not suggest you to use this method. Just list the table. Use that one. See, each time you should find the Z score for the X value and the Z score for the Y value, which means for the individual value, you should use the Z formula. So it's not easy to calculate, but you will get the same answer. Now, if we increase the sample size to 23, the same example, but this time we add more pairs into our sample. We will total have 23 pairs. And if we add more, at last we got this R. R is equal to 0.801. So we will say, is there sufficient evidence to support a claim there is a linear correlation between these two variables, chocolate and the Nobel Prize? So actually we need to do hypothesis testing, then we could make that conclusion, but we will skip the hypothesis test part. So we will just skip the hypothesis test part. Maybe for, let me see if there is. Okay, we will skip the whole hypothesis part. Just check the interpretation of the R. So from the previous result, if we use 5 pairs of data, we will have 0.7795. But if we use the 23 pairs of data, we will get 0.805, right? We know if we have this as our R value, we will use the R squared to explain the linear relationship between X and Y. We will use the R squared value. So let's check. If this is the R value, then we're going to use the R squared value to explain the relationship between X and Y, linear relationship. So if R squared value is 0.642, we will say about 64% of the variation in numbers, this is our Y variable, can be explained by the linear correlation between between X and Y. So we will use the R squared value to express the linear relationship between X variable and the Y variable. Okay, that's how we interpret R. We do not directly use the value of R. We actually use the R squared value to interpret about 64% of the variation of the number can be expressed or can be explained by the linear correlation between X variable and the Y variable. So here we will have a common mistake. The correlation just tells you there is a linear correlation between two variables. But correlation does not imply causality, right? It's not necessary to be the cause-effect relationship. It's just the linear relationship. Just like this example, the variable X says the chocolate consuming. But the Y variable says the Nobel Prize. There is a linear correlation between the chocolate consuming and the Nobel Prize. But it doesn't mean if we consume more chocolate, then we have more probability to get the Nobel Prize. Right? If you think that's the cause and effect, that will be ridiculous. So we will say the correlation, linear correlation does not mean the causality. Okay? So if we consume the correlation implies the causality, that's the error. That's the error. Okay, and we cannot use the data based on the average. If we use the data based on the average, then it still will make mistake. We should use the individual value, okay? And the last one is sometimes we just ignore the relationship, a nonlinear relationship. We can only see there if the value is very low, right? If it's a very low value for the R and for the R square, we could only interpret that there's no strong linear correlation between X variable and the Y variable. But we cannot get to the conclusion like that there's no relationship between X and Y, because it's still possible to get a nonlinear correlation, because R only measures the stress of the linear correlation, but it cannot explain the nonlinear correlation. So our conclusion is just about the linear. We cannot get any conclusion about their nonlinear relationship. Okay, so that's for 10.1.